Are there any other questions about the homework assignment that was due today? I've instructed the grader, who you met, George, to give you a more severe grading if you haven't gone to the writing center. So if he has to stare at your stuff for more than 5 minutes in order to decode it, it's an automatic 70. So I say you must be able to write clearly because this will serve you throughout your adult professional career, especially if you plan to seek employment here in the United States. Because people will call me on the phone and they'll say, so-and-so is not able to function within an English language speaking culture. And I'll say, I'm very sorry to hear that, but what can I do about it now? And so in order for me to place you in various positions, you need to be able to write reasonably well. I spoke with Mary Kleps, and she said that some of you have applied for positions and your cover letters indicated that you were having a lot of trouble with your writing. And so this is one of those things where I think it reveals something that does not speak positively for you if you're applying for positions. So you need to make sure your cover letters are correct when you're applying for positions, and you may like to use the Writing Center for that as well. Especially if you're not sure how your cover letters are being received, or if you're not able to get reasonable job offers in reasonable time. Somebody had better look at your cover letter. Somebody had better look at your resume. It's very important that these things look clean and professional. So when we go into this next homework assignment, again, I'm going to ask that you revise your problem statement and that we add another section. And this section is called your approach to the problem. Does everybody understand what it means to approach an engineering problem? Is it clear? The problem statement is different from the approach, but your approach to the problem will be perhaps something that you will use as a technical solution. So stating the problem and stating your approach to solving the problem are very different things. Right? I've got a problem, and my problem is people keep calling me on the phone and they bug me, and they're telemarketers, and they keep calling, and I say, don't call me anymore. It's terrible. You're bothering me. That's a problem. And to solve the problem, I am subjected to the constraint that I do not wish to completely disconnect my phone, because then no one can call me, and I cannot call anyone else. So my approach to solving the problem involves using a call blocking service provided by the telephone company, and I can go and proceed to block individual phone numbers. And so if a phone is identified, then it will block it. And then I said I will block all phone numbers that don't identify, that is, those which are anonymous. And so then certain people cannot call me because they refuse to identify their phone number, but that is a nuisance, but it's okay because I can greatly reduce the number of telemarketing calls. So you have a problem, and then you have an approach to the problem. Very different things, you see. Does everybody sort of see where I'm coming from on the approach? So you guys are going to be making progress toward a thesis proposal. And that thesis proposal is a laudable goal, because what it's going to do is it's going to enable you to articulate in writing a proper problem statement and a proper approach to solving the problem. And being able to do these kinds of things is something that will serve you throughout your adult professional careers. It's not a specific skill. It's what we call, in engineering, a soft skill. Right? But these soft skills are so important. Right? And so, in some sense, I say this may be one of the most important, generally, courses that you're likely to take because of its impact on your career. If you can't get this right, if you can't get the communication skills right, it will adversely impact your ability to get jobs. It will adversely impact your ability to get a promotion. It will adversely impact your ability to call the shots in your research. So, in other words, for you to be technical leaders, you're going to have to communicate well. You will have to be able to speak in front of others with confidence. You'll have to be able to describe problems and the approach. And when you do describe those problems and their importance, then within a company, they can free up resources, other people who will come to work for you because you've been able to pitch the problem and successfully take ownership of the problem. And so this is a key element. In entrepreneurship, you have to be able to pitch the problem as part of your business plan. This is a problem we intend to solve and monetize. And once you are able to do that, you can free up funds from venture capitalists and angel investors. So being able to solve basic problems, so important. And stating them well and describing why these things have impact allows you to sell the value which you have added by solving the problem. That is to say, solutions to important problems add value to society. So that's one of those things I think, you might like to think about. Some people might say, maybe the approach is part of what you call a research plan. Right? What do you plan to do to solve the problem? If it's the case of identifying a disease using healthcare informatics, as Tarek was talking about, maybe the plan is to start doing a little data mining, healthcare informatic data mining, in order to be able to determine where the diseases are and what they might or might not be correlated with. That's not an unreasonable plan. But your general approach to solving the problem is not the same thing as, let's say, a detailed research agenda with a list of experiments. Right? You're not there yet. Right? So you're not able to make a detailed research plan. But what you can do is you can generally describe your approach to solving the problem that you've stated. And you should be able to do that. I think you can. Let's see if we can create some interesting content here. I'd like to be able to scroll to the left. Course content, assignment. Let's call this one Homework 3. Restate your engineering problem and add a section. And the section should be called Approach. And in the Approach section, I'll say describe in general terms how you intend to solve the problem. So I'm giving you a whole week to think about and write about your approach. In the process, you may decide to revise your problem statement. Whoops. It's my trackpad. Sorry. Does that mean you could completely change your problem? Change your mind about your problem? Go to a completely different problem? Yes. If at this point, in this very early stage of your proposal, you say, you know what? This idea of just doing something with healthcare informatics isn't specific enough, and it isn't going to give me the ability to state a valid engineering problem because I don't think it's going to give me the ability to solve something so general. Then you might narrow it down to the point where you just talk about one kind of cancer or one kind of disease or one kind of electronic record. And I think, right now Tarek's problem is probably a little too broad, but I might be wrong about that. I think it is. So revising the problem might be very good. It might really save your thesis proposal. Somebody else have a problem they'd like to share with us? No. Really? No one wants to share any problems? I'm going to call on people. Let's see now. Riti. Not here? Huh? Riti? Oh, you're here. What's your problem? Riti, what's your problem? Can you just quickly tell us? Short problem statement? What? I'm sorry, I can't hear you. You've got to speak up for me, please. Should I get up? Is that? Hey. You're first on my list. I'm picking on you because you're number one. You won't do this again. Next time we'll get someone else. What's your problem? You're gonna tell me later? Yeah. Okay. Tarek just walked out. But he already told us his problem. Let's see now. Enurup Pashetti? Pashetti? Enurup, are you here? Absent? Sairam Bera? Yes, Sairam, what's your problem? What problem did you decide to discuss? What's it called?
Embedded web technology.
Embedded web technologies. Okay, and so you're going to build a kind of networked embedded system, is that right?
Yeah.
Okay, and so what is the problem that you want? I see the problem domain, networked embedded systems, very good. What problem do you want to solve with that?
You can control embedded devices remotely.
So you are given embedded devices subject to the constraint that you control them remotely. What do you want to find?
We can interact with the embedded devices at any place using just web browser.
You want to find a way to control embedded devices using a web browser.
Yeah.
Don't they have that already? You can. A printer is an embedded device. It sits on a network, and I can go to my web browser and I can find my printer. So what you're doing different? What problem are you trying to solve that's not already solved?
We can use embedded server to any embedded device. You can connect the embedded server to devices like household devices like washing machines, ovens, anything.
I can see the value of putting the washing machine on the network, because then it can warn the dryer about the dirty underwear that's coming. But suppose you were to tell me that your goal was to network a specific device, like the washing machine. Is that your goal? You want to turn the washing machine into a networked embedded system? Network the dryer and the washing machine.
It's not only limited to washing machine, but many long term is the single device system.
problem statement that needs sharpening, because networked embedded systems is a domain area. It's an area, a course which I could teach and which I have taught in the past, but it's not a problem statement. If the problem is to network devices, it's very good if we know what kind of devices you're trying to network. So maybe what you'd like to do is sharpen that problem statement into a domain that makes it a little bit more what I will call tractable. So if you said, I want to network power strips so that we will know how much power each one of the power strips is consuming. So now I want to find a way to convert power strips into networked embedded devices that monitor power usage, so that anyone who plugs anything into these power strips will be able to keep track of the devices and their power consumption as a function of time. That sounds like, a proper sort of product that solves a very interesting problem, tracking power usage as a function of time in the household. So now instead of kilowatt, which only gives me an instantaneous measure of power usage, I can see power usage as a function of time. I could network it back to my iPhone. And now I can go to my iPhone, and the iPhone can say, hey, red alert, you left these cell phone chargers on all week long. And believe it or not, they used 100 watts of power every hour. And that added up to, let's say, 7 kilowatt hours of power. That just cost you $1.50. You should turn these things off when you're done. Right? That's important information. So if what you're trying to do is track your electric costs by creating a networked embedded system that essentially takes your problem statement and targets one specific thing. Say it again?
Narrows down my problem.
Yeah, it narrows the problem, makes the problem tractable. So make sure your problem is small enough to be solvable, but large enough to be important. So the problem, let's say you're just going to do networked embedded systems for power strips. That's a very small problem, right? That's a tractable problem. I could build something like that within the course of a 2-semester thesis. And I could have a proof of concept prototype. I could even try and get something like a Kickstarter project and sell that and monetize it. And maybe, because it's a power strip that anybody can plug anything into, that's important enough to care about. And maybe, if I could get a patent on it, I could have a sustainable competitive advantage, which I could then license to big companies or sell on Amazon. So now you have not just an important problem that a lot of people care about, you have a potential product around which you could build a business. There's that entrepreneurship thing. Does everybody sort of understand about what it means to narrow down the scope of your problem so it can result in something that you can really do? I mean, it can't just be, I'd like to do something about networked embedded systems. That's nice. But if you just want to learn about it, take the course, right? Or read a book. So we'll allow unlimited attempts. And maybe what we'll do is we'll set up a due date in 1 week's time, and we'll set up a time. It's 5 p.m. and all students will get it. Alright, now before I hit submit, restate your engineering problem and add a section on approach. I'll just write on approach. So now you're going to have an approach to your problem. Everybody sort of understand this? Okay. I'm hitting submit now. We have a proper approach. And it's another homework. And the prior description of what an approach is, I mean, these are kinds of questions that you may or may not be able to answer directly. You may not know right now about the originality of your approach, but your papers, which you're researching, will tell you if others have tried this before. For example, I suggested that you have an intelligent power strip that's networked. Gee, wouldn't it be swell if nobody ever thought of that idea before? So, a networked power strip. Oh, look, network-controlled power strip. Uh-oh. It's been done. Oh, no. Award-winning power strip called Quirky. IP-managed remote power strip. Oh, dear. Oh, look, it has Ethernet interface. Oh, no. Someone did this already. Oh, but maybe your power strip will be just like them, except there'll be a difference. And the difference is an iPad app. I don't know. I made that up. IP-managed power strip. Somebody thought of this already, so you'll have to go on to the next idea. Maybe this isn't the right idea yet, but you may be coming close. Oh, look, you can even buy them on eBay. What else? Any other questions? Shall we try another person? Let's see. Let's try VJ Bonapali. Is VJ here? Absent? You're here. Ah. What was your problem? Okay, so you would like reliable communication between a transmitter and a receiver. And in order to do this, you are going to impose some kind of error control. So now you can do this in two ways. One way is forward error correction, and the other way is backward error correction. With forward error correction, you can have error correcting code, which is corrected at the receiver without any backward transmission. With backward error correction, you can detect an error and ask for retransmission events. So, which one did you want to do? Forward error correction or backward error correction? You don't know. Which way? Forward. Okay, so error correcting codes have been researched and described in the literature, and I dare say that if I typed in error correcting code, you will get 2.7 million hits. So maybe we need to somehow narrow this down. Is there a specific domain you want to describe? For example, voice, or just data, or video, or just data. So if you're just going to do error correcting codes and data, you have your work cut out for you, because there are many error correcting codes. And then the question will be, which ones do you think you're going to use, and why? Is your data? Do you know anything about the channel? For example, when you transmit, are you transmitting your error correcting code in a noisy channel where the noise is even, or is it going to be bursty? For example, if you're going to record something onto a CD, you might have areas in the CD that are dirty, so you might have bursty data loss. Whereas if you're going to just use some kind of transmission that goes over the phone line, maybe the noise is just general and Gaussian. So do you know what kind of noise you're going to have? Will it be bursty noise? Do you know where you're transmitting? Is it radio? Yes? I beg your pardon? It's a system transmission. But where is it transmitting on? What's the physical layer? Is it transmitting on wire? Or is it transmitting in radio? Or is it transmitting in sound? How does energy propagate with this system? You're not sure. I think it'd be really good to know. I think if you're going to narrow this down to make the problem tractable, you should say, I'm just going to worry about error-correcting codes for magnetic tape, or for, whatever problem domain is interesting to you. Sound over a telephone, or a line, modem. Or maybe, we do error-correcting codes for Voyager. Voyager is a satellite which communicates to other dishes, and the dishes are all over the planet. The Jet Propulsion Laboratory runs what's called the Deep Space Network. It all focuses in on Voyager. As Voyager encounters other planets and then proceeds to leave the heliosphere, it still can transmit back to us. It's powered by plutonium thermopile batteries. And there are 3 of them. And they're still fully charged. And they will be for the next 2 years. And there's 2 Voyager satellites, both transmitting back to Earth. But Earth is just a tiny little dot to Voyager. And so to see these signals come in, you need error-correcting codes. And so the data rates are very low. The power is extraordinarily small. But if you have all of the dishes pointed at Voyager, you can still receive it. You can still hear it. That's remarkable. And it's because of error-correcting codes. But consider that it is an open-loop transmission. It can never retransmit. Voyager cannot hear us. And so as a result, if we miss the data that comes back because we couldn't decode it, it's gone forever. So that kind of forward error correction has been created specifically for Voyager, specifically for a very low power transmission over a very long distance. And so that kind of error correction solved a very important problem with very high impact, because it's the only artificial satellite that we have here from planet Earth that has gone that far away. So I say, let's narrow that problem down. So we talked a little bit about outlines before, and right now what we're doing is we're building subsections of our outline. And I think I might have mentioned I write books, and when I decide to use an outline, I can be very productive and can get the books done on deadline. And when I don't use an outline, I get myself into terrible trouble. And right now where you're at is in the problem statement, and where I'm hoping that you'll be is in the approach. After that, I think what we'll do is we'll discuss the motivation for the problem, why this is an important problem. But it sounds like a lot of you still need to narrow down your problem statement. You still need to get it so that it becomes tractable. How many people here feel like they have a tractable problem statement? Yes? Almost tractable. But nobody else. That's a big problem. You have to be able to solve this problem in given time. And the given time is 2 semesters. That's it. You're done. So if you're thinking about doing a thesis proposal that can be done in 30 weeks, this has to be a problem that you can solve quickly. It cannot be one where you just mess around and try and figure out what problem you're trying to solve is. Right? You need to know. So, what's a body of knowledge? We covered this earlier today because it was Tarek's question. Did everybody hear his answer? What's the body of knowledge? Maybe the body of knowledge is error-correcting codes. Right? There's a lot of paper written on error-correcting codes. But if you're really focused on one kind of error-correcting code, something that has to do with, let's say, block coding, that's a pared-down body of knowledge. If you said to me, I'm going to be working on an area of error-correcting code that's very specific to, let's say, audio on the phone line, right, where we'll use modems, what are the principles that you're going to consider? The big picture principles. Well, you might say, I'm interested in phase amplitude modulation for encoding different signals in order to make a receiver that can detect individual points in a constellation of phase amplitude modulated points. And so that may be a basic principle upon which you build your decoder. Do people care? Why should people care about communicating on a phone line? Well, maybe people still have to do that. Maybe that's still an important thing to do. And so there's great impact for it, although modems have kind of lost their market share because people want broadband. If you do come up with a better solution for communicating over the phone line, how will you communicate it so that others will be able to make use of your work? Maybe there's an algorithm that you can state elegantly and others will be able to implement that algorithm. Perhaps you could even implement the algorithm yourself in some high-level language and then say, you know, others could do this maybe in VHDL, in some hardware language, and thereby implement it in hardware and make it run much faster. In other words, if you have an algorithm that works really well but needs a lot of compute power, maybe it's possible to implement it quickly if somebody wants to take your research and make hardware, make chips. And if they make the chips, they can do this decoding. So solving the problem might just be the first step. And maybe there's a step that comes afterwards where they say, we have a solution and it's really good, but it's slow. And now someone has to take it and make it fast. Well, that's very good, because now people know exactly how to solve the problem. They just don't know exactly what approach to take in order to be able to make it a fast solution to the problem. And so then if you said to me, well, after they build the hardware, they'll be able to make these inexpensive chips, the implication is people will be able to communicate with a phone line without spending lots of money at the cable office. They don't have to go to the cable company and buy high-speed internet anymore, because they can just make a phone call and the phone modem will be just as fast. Right? Wouldn't that be great? And here comes the approach, and this is the part where I think you guys are going to have to make some hard choices. What are you going to do to solve your problem? What will you design? Or what are you going to implement in order to be able to provide a solution to your problem? You know, if you told me, well, my problem is I really need a beer. And I need a beer every morning, and I find it very difficult to get up in the morning until I have my beer. So and I really like robots. I like beer and I like robots. So I have a solution to my problem. It's called the Beer Bot. And it's a robot, and I program it to bring me my beer. You might just get a significant other who could bring you your beer, but nobody could stand you because you're always drunk. That's too bad. But the robot will be your friend and will bring you your beer. And the robot doesn't care if you have issues with showering. So as a result, when you finish with your thesis, you'll have this wonderful robot, which you could probably sell online. Wow, you could monetize it, the beer bot. And it goes and it brings you your beer. I think people would buy this. People like robots and gadgets that do these things. The beer bot. And so if you want to, your approach to the problem will be to design and construct your beer bot, which brings you your beer.
If a really lazy person, that person does not buy the beer for event. He has to operate the beer by event to get the beer. He is very lazy in the morning and he cannot operate the beer boy to get the beer.
Well, the beer bot could wake him up with the beer.
Oh, that's right.
So you could say, beep, 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 here's your beer. And you can say, oh my God, I'm so glad I can wake up now. Because the only reason you get up in the morning, maybe it's not beer, maybe it's coffee.
Oh.
But it's because you're students, I thought maybe you like beer. And because you're engineering students, I thought maybe you like robots. And so then I said, well, I'll make it a beer bot because then that's the best of both. But it could bring you your coffee or your tea, and then, of course, it's not as interesting to college students who like to drink beer. Let's see now. So my approach, I have to build hardware and software, right? That's just like a computer engineer. He uses both. And what are the implications? If you can bring a beer, maybe you could also go out and get the newspaper later, right? Later, after a few months of extra development after the thesis is done. I'm not going to try and solve those problems, but for future work, I'd like it to bring me my newspaper so that I can read it while I drink my beer. So I think maybe it would be very good to use the robot for other things later. But just for now, if it can just bring me my beer, I'm happy because I'll have my beer. Now, there may be other, I'll call it robotic literature, right? Lots of people have written about robots. And my robot is just like their robot, with a difference. My robot brings me a beer. Their robot, maybe it vacuums, maybe it helps people, maybe it builds cars. My robot is different because it brings me a beer. That's different enough. And so if you said, well, somebody built a robot that brings a newspaper, say, well, a newspaper is nice, but I'd rather have a beer. And so that's okay. It's different enough if no one has got the beer bot to bring you your beer, then that's sufficient. And one thing I could say is that's a sufficient amount of originality. But when you do your historical review, you'll say, so-and-so built a robot that fetches a newspaper. And that's just like my robot with a difference. And the difference is it brings you a newspaper, whereas mine brings you a beer. So you could say, is that a rigorous thing? I don't know. Rigorous enough. What would be the approach to constructing a robot that brings you your beer? Yeah, maybe it has wheels. Maybe it has a gripper. Maybe it has to open the door to the refrigerator. That sounds hard. Or maybe you have a special beer dispenser that's at the robot's level on the floor so it can go and get the beer. That might be a way to make it a more robot-friendly beer dispenser. So if you had a robot-friendly beer dispenser, maybe it solves a lot of problems. That's a good approach. So when you sell the robot, you'll also sell the special kegerator. Oh, the robot stores. Well, it makes the robot very heavy if it has to bring the whole cooler with it. So it goes to the special beer cooler, which it comes with the robot. That's an optional accessory. Grabs the beer and then brings it to you. Beer bot. I like it. Now you could say, very few people have a robot-friendly beer dispenser. So that's part of the originality of the research. What are the ethics of supplying somebody with beer while they're kind of just waking up? They're promoting alcoholism. Does this sound like something that's contributing to societal good? I think there is value added in having a discussion about ethics. Ethics for a profession like engineering consists of a code. For the IEEE, we have an IEEE Code of Ethics, which gives us a list of rules of behavior for those things which are considered to be ethical and those things which are considered not to be ethical. In the world of the legal system in this country, the ethics have the power of law. If you as a lawyer break your code of ethics, they can put you in jail. They can disbar you. They can sue you. So ethics for a lawyer are a big deal. Ethics for an engineer don't necessarily have the power of law. In general, I rarely hear of an engineer who loses their license because they were unethical. But it could happen. They have a special PE license, a professional engineering license. Everyone here should have a code of ethics. In general, I would say it is an IEEE Code of Ethics for people in the ECE program. If you were a mechanical engineer, I'd say it's ASME, American Society of Mechanical Engineering. Maybe it's the association. No, I think it's American Society. There's probably an ASME. There's a JSME, Japanese Society of Mechanical Engineering. So every country probably has its own code of ethics for mechanical engineers. It's not international. Not that I know of, anyway. Who here feels like they're more like a software person? Like to write programs? Nobody? Because there's an ACM, an Association of Computing Machines, and they have their own code of ethics, which is different from the IEEE. So what about the research? Is it possible that it could be safe? Right? Here's that robot. What could possibly go wrong with a robot that brings me a beer? I could step on it while I wake up after drinking an entire beer. And I'm a little drunk, so it's quite likely I'll step on it, and then I'll fall over and crack my head or something. Serve me right for drinking so much. So there's a safety consideration here. I could then sue the manufacturer of BeerBot. That's you. And probably also Professor Lyon, who gave you the idea. And then proceed to say, look, this is not a good idea. Beverage bot. Oh, yeah.
So the user determine what type of beverage they want.
Well, suppose it doesn't bring, it doesn't bring a beer. It brings a soda. Maybe it's okay. It's less evil, I guess, or something. Well, it could be a diet soda. It brings you a diet soda. That's not supersized and doesn't come with fries. So maybe there's a compelling argument that people need to think about the safety considerations of whatever it is you're building. Somebody told me they wanted to do a smoke detector that didn't need a battery and it would stop chirping. And they said that's part of their low power energy harvesting project. I have a senior project team working on this now. I said, well, what happens if it fails and the house burns down? You could get sued, big time. This is a big deal. So you have to think about the ethical implications, the safety problems. You build a safety device like a smoke detector, it's a problem if something bad happens. I have, suppose the simplest thing. Let's say you build a refrigerator and it has a couple of 40-watt light bulbs in it, and the light bulbs don't turn off when the door closes. That could heat up, melt, cause a fire, spoil food. It's a big deal. So you've got a safety issue, right? Because now you've done is instead of a refrigerator, you've built an easy bake oven. And now you're starting to order papers. And the papers are going to start coming in. And you're going to have to start reading these papers. You've already ordered 10. I suggest that you order another 10. I suggest that these 10 papers that you order, that you've already ordered, have started to come in, and you should start reading. It's a readings course. So you're all going to have to do lots of reading as well as writing. Every time you read a paper, answer basic questions about the paper. How does this relate to what I care about? If it doesn't, don't cite it. Not every paper will be good. What did they do if it related to my field? What did they do to contribute? Why do I care about this paper? What are they claiming? And does it sound like what they're claiming is true? Is this a valid claim? How do I know if the claim they're making is true? Is there good data? Did they back it up? You need to think critically when you read papers, because not every paper that's been written is going to contain correct data. There's a thing which people call validation. That means that you're going to state the experiment that you intend to design, that the data that you collect is either going to validate the hypothesis or invalidate the hypothesis. I think I gave an example to Tarek where I said, well, maybe you'll have a hypothesis that says the water is causing breast cancer. Well, how would you test that hypothesis? Maybe you design a survey, and the survey says, do you drink bottled water or do you drink from the tap? And have you had any cancer? Or do you smoke? Right? A couple of questions like this, and you broadly run the survey, and then all of a sudden, maybe it's possible for you to determine whether or not your hypothesis is correct. And then when you have a proper research validation proposal, you can come up with a research agenda, the milestones. And remember that these milestones are basic things that you intend to be able to do, like design the survey, administer the survey, collect the data. And once it's done, you should be all finished with a write-up in time to get your thesis finished in 2 semesters. Otherwise, you don't have a reasonable timeline. So it's often the case people have an aggressive timeline. They think they'll get things done much faster than they actually can. There'll be a midterm in this course. Typically, it's more than 6 pages long. By then, I expect that you'd have 22 papers that you can actually cite, useful papers that you want to write about. And you're going to write a little bit about each paper. And a little bit could be a paragraph and a half. Just a little, a few sentences. And presumably you'll have a problem statement, and you'll have a table of contents. That's what TOC stands for. And it's probable you're going to need at least a dozen pages. So the writing that you're doing now about your approach, that's going to be a part of this midterm. That problem statement that you did in Homework 1, that's going to be part of this midterm. Those papers that you ordered last time and that you will order for next time, they're going to end up being part of this midterm. Keep ordering papers that look like they're going to be interesting for you to read. Right? If you find it's boring now, change your subject. Right? If you're bored now, you're doing the wrong thesis. Right? So this is actually a pep talk. How do you know when you're doing the right thesis? You're excited about it. It's interesting. You want to read these papers. If you see it as a chore, you've got the wrong thesis. You say, oh no, another paper on networked embedded systems. Oh my heavens. Change your topic. This is the time to do it. Because by the time this course is done, you're going to have a thesis proposal. And if heaven forfend, you embark upon a thesis that you don't like, you're really going to hate yourself by the time this thing is done. You'd probably hate me by even worse. So I say make sure that it's a thesis you're interested in. And now I get to give you the talk about advisors. In your academic career here at Fairfield University, you will have a curriculum advisor. That's me. Okay. You'll also have a thesis advisor. That might not be me. Right? You might say, I really want to do this thing about nanotechnology. Great. I got the guy for you. He got his PhD from Yale University in nanotechnology. And it ain't me. And he's Dr. Munden. If you said to me, I really want to do something in communication systems with error-correcting codes, I'd say, I got the guy for you. And he's Dr. Denenberg, and he's upstairs on the 3rd floor. So he can help you. Right? He's a guy who will be able to say, I'm real familiar with that literature, and guide you in the right direction. So finding the right thesis advisor is very important. You cannot do a thesis without a thesis advisor. So somebody on the faculty is going to agree to be your thesis advisor, or else you can't do the thesis. That's so important. So pick a thesis you're interested in, and then we'll figure out who your thesis advisor should be. Doesn't have to be me. We talked before about taxonomies. Taxonomies were going to help you to organize your literature. So when you see the papers coming in, you'll say, oh, that's a paper that is on backward error correction. That's a paper that's on forward error correction. 2 different areas. So in the world of error correction, I got 2 kinds of areas. Forward error correction, backward error correction. I can categorize my papers this way. This allows me to categorize the body of knowledge that I'm interested in. And if I say I'm only interested in forward error correction, I can ignore those other papers. I don't even have to write about them. I can say, that's not in my field, that's not the area I care about. You want to get real focused. In the world of control systems, you might say there's a body of knowledge in control. Classic control and modern control. And in classic control, there's heuristic control and stability analysis and transform techniques, which you might learn about if you study control theory. With modern control, there's intelligent control and optimization theory. And within intelligent control, there's fuzzy control and neural network control and hierarchic control. Hierarchic control has increasing precision, decreasing precision with increasing intelligence. So you have microcontrollers that control things at a higher and higher level, whereas at the joint level you might have a simple joint controller. At a high level you might have something that does spatial reasoning about the environment. So your taxonomy organizes this body of knowledge, and in so doing allows you to organize your papers. Because once you have this taxonomy, you can create an outline which allows you to write about the individual papers in different subsections. And so the taxonomy helps you to create a kind of table of contents where each sub-area inside the table of contents allows you to group your papers together. So grouping, which is something that Jackie talked about last time, grouping is a way in which you can take your papers and say, these are all related. They all stick together, and they're all about the same sub-area. And you'll probably make a contribution to just one sub-area, because your thesis will be focused, and your problem statement will be tractable. Taxonomies in Java are known as class hierarchies. Class stands for classification. When you have a classification system, you have a broad set with a number of elements. The number of elements in a set is called its cardinality. The reduced subset has a reduced cardinality. The set of all animals is quite large. The subset of mammals, because mammals are kinds of animals, is quite a bit smaller. The subset of ape-like animals is smaller still. So if you think about the cardinality of the set, the subclass or subclassification, you're looking at C++, Simula, C#, and Java all as class-based or object-oriented languages because they use that classification system. So these are models of a body of knowledge that's been organized using a directed acyclic graph. That is a kind of hierarchy, where you say a mammal is a kind of animal, a human is a kind of mammal, and every time you use a kind of, you're saying it's a subclass. So here's the animal. What kinds of animals are there? Well, it could be a mammal, it could be a fish. Right? So the set of all mammals is quite a bit smaller than the set of all animals. And the set of all fish is quite a bit smaller than the set of all animals. And you can have a human, which is a kind of a mammal, which is a kind of an animal, and you can have a mollusk, which is a kind of a fish, which is a kind of an animal. But you can't have a human mollusk, because that would be an example of a non-tree-like relation, right? In a tree, the leaves of the tree don't arc across. They stay solo. The branches don't arc across. So a directed acyclic graph has no cycles. If it had cycles, then you could have arcs across. But the directed acyclic graph, which is represented by the taxonomy, doesn't have that. And that's why you cannot have a human mollusk. However, here in the new age of genetic engineering, it might be possible. We could take mollusk chromosomes and insert them into the human genome and make crab people. They'd probably be good with butter. Crab people. So I'm thinking, yes, it's possible to violate this. You create a new species. Maybe you'd have to have a new branch in the taxonomy. What do the crab people do anyway? I'm just sort of thinking out loud. They sit around and they ask their beer bots for beer. The crab people. Ah, boy. Sorry, is it getting late yet? Oh. So, as I'm thinking about this, if you think about sensors, right, in robotics, there are two kinds of sensors in the world, active and passive. Passive sensors are ones that use the energy around them without emitting energy, whereas active sensors, they basically use energy in order to illuminate their environment. Radar is an active sensor. It uses a chirp in order to be able to identify its target. Sonar uses a ping, just like radar, only it uses sound. Let's see, what's a good passive sensor? Your eyes. Your eyes do not emit laser beams in order to illuminate the target. Your eyes rely upon the energy in the room in order to see. So your eyes are passive sensors. Well, what if you use a flashlight to illuminate the room? Well, now it seems as though you've transmogrified your eyes from passive to active, because without the flashlight maybe you cannot see because it's too dark. So here's how I divide up a taxonomy in the literature. Right? This is acyclic graph. Right? So I see there's two kinds of robot vision systems, 2D and 3D. I see there's direct measurement and indirect measurement, and I care about direct measurement, and I call it metrology, because that's the field. It's body of knowledge. And in metrology I have ultrasonics, but I don't care about that, so I don't explore it further. And then I work on optical metrology. That's my area. So my optical metrology field allows me to do direct measurement for 3D robot vision systems. I can measure stuff in order to be able to do quality assurance. And now I can do basic things. I can illuminate my target with LEDs, with lasers, and I can use what I care about, the area that I have my patent internationally, diffraction profilometry, which is very specific subtopic. so specific that you can say, aha, I've made a contribution to the body of knowledge. That body of knowledge is in robotic vision systems, specifically 3D direct measurement optical systems. And so now I have a whole new area called diffraction profilometry, which didn't exist before. So I'm making a contribution to the field. And it's clear where that contribution lies relative to other contributions. So once we get into this midterm, and it'll happen surprisingly quick. 8 weeks into the semester, it'll happen. That's 5 weeks from now. You'll have an idea which will be packaged. All the things that you have, you'll have to combine it in a way that makes it palatable so that you can sell your idea. You'll need that writing to come up to speed. We've seen terrible writing so far. That's going to have to improve, and quickly. And so if there's a lot of blemishes and a lot of grammatical errors, I think that's going to be a problem. I'd also like to say a word about coming to class late. I don't know if you noticed it, but the way they designed this room, the door is in the front. And you cannot help but walk in front of the lecturer when you walk in. So I say, please come on time, because otherwise it interrupts the lecture. Today we had a guest lecturer. It doesn't look right when a guest lecturer comes in and the classroom consists of perhaps 2 or 3 people in the front, and I know there's supposed to be like 18 people in this classroom, and then people saunter in, a few minutes late. That's not cool. So, I mean, it seems almost a little rude. And I know you don't want to be rude, and I know you don't mean to be rude. So it's forgiven. But in the future, I think it's very good if you can come in on time. I will start on time, and I think it would be very good if you're going to come in not to be murmuring in the back of the room, because I hear it, and it's very distracting. And if you have a question, I'm very happy to have you speak out and interrupt me, or raise your hand if you prefer. Don't stand on ceremony and let your question, sit, because that's not good. And you'll forget the question, or you'll think it's not important. If you have a question, probably 3 other people, maybe more, have the same question. So ask the question. There's no stupid questions. So don't be shy about asking questions. As far as the proofreading is concerned, how many people here have used the Writing Center? A big mistake. It's free. They are there to help you. You should definitely go there. Have people look at your stuff, especially if I gave you a comment, or if the grader gave you a comment that said you really need to go see the Writing Center. Because at this point, I think we've been very patient. It's 3 weeks into the semester. If you're not going to the Writing Center now, it will be reflected in your grade. I've asked the grader to do that. So, if you know that your writing might not be good, or if you were told to go to the Writing Center and you didn't, it might be good to go to the Writing Center tomorrow. Get your stuff proofread. Maybe resubmit it before the grader gets to it. He'll probably use your most recent submission rather than the one that you submitted prior to the beginning of class. Just get it fixed. This is your opportunity. So, proofread your stuff or get it proofread. Me personally, I don't know if you do this, and I learned this from my advisor when I was in school, because my writing wasn't great when I was in school. Print it on paper. Get your cup of coffee or your beer and sit down in your easy chair and red pen your own work. Be your own proofreader. It's surprising how many mistakes you will find if you do that. And when I write books, this is just how I do it. When a chapter is done, I print it and I go through it and I red pen it. I'm my own copy editor. And I think objectively about my own stuff. And then I go through in front of the computer and I type in the changes. Right now you have very little written, so it's not that hard. And it's very good if you can proofread your own stuff. But if in the event that you can't, you should definitely go see the Writing Center. Does everybody know where that is? Yes? Yes? Okay. So this goes to the basic question of what's a good enough problem. It can't be trivial. It has to be narrow in scope. It has to be doable. That's the most important thing. You have to be able to finish. Things that you try won't work. What will happen when they don't work? What will happen if you have bugs in your software, or if you can't get good robotic systems to bring you a beer? How will you salvage your proposal? Planning milestones that are too densely packed with deliverables, that's a big mistake. You get too aggressive with your research agenda and it will sink you because you won't be able to keep up. And at the end, we're going to have a conclusion, right? This will be when your thesis is done, and it'll talk a little bit about your results, topics for future work, and then comes a subsection called the literature cited, and that's your bibliography. That's all the stuff that you talked about in your historical review. And so once you've got your taxonomy set, you're going to end up creating an outline for your historical review. And remember that taxonomy was tree-like structure. It's still a tree-like structure, but now it's cast out in text, linear, top to bottom, left to right, with indentations. And those things enable you to see the branches in the tree, and it allows you to organize the literature as you encounter it and put it in the right subsections. EMF, by the way, stands for, anybody know? Force, electromagnetic force. Some people would call it, or electromotive force. I call it electromagnetic force. This is high performance APIs, or application programmer interfaces, libraries. And so for accelerating Java, I could say there's vectorization, and then there's assembler, and then there's distributed computing. When you look at your work, look at the work of others, figure out how they designed their solutions to the problem. What will you do to do your design? Will you simulate? We have a project now where the students are designing antennas. First thing they do is they simulate the antennas. Then they build the antennas. Then they measure the performance to see if their simulations are any good. And guess what? They're close, but it's not exact. They want an antenna that's supposed to work at 2.4 gigahertz. It runs at 1.9 gigahertz. Why? Well, because the simulations didn't take into account the dielectric properties of the printed circuit board. So it acts like a big capacitor. And the parasitic capacitance of a printed circuit board is important at 2.4 gigahertz. It's a transmission line. So it wasn't anticipated by the simulator. It wasn't programmed in. So you've got to validate your simulations with a direct measurement. And now they have to go back and change the design and do another prototype. So you have to afford yourself a little time for iteration. These things take time. It takes a couple of weeks to get back new printed circuit boards from the manufacturer. So that's what I have here for today. Are there any questions? No one will ask questions because they know that it will delay their departure. Anyways, I hope you got something out of the lecture today. I very much enjoyed Mary Klepp's presentation. You now have the lesson on how to make sure you get notifications from your Blackboard system. That's so important because I've gotten emails from people that said, I didn't know there was a homework, and they didn't check. And gee, if they had their notifications set on, they would have gotten at least an email. I find the idea that the computer will call me with text to voice a horrendous notion, because I will get up at 3 o'clock in the morning and I will add something to your homework, and then your cell phone will ring and it will say, "Oh, you have an extension on your homework," and you'll be like, So I don't think that's a very good idea. I think that's terrible. I don't want computers calling me in the middle of the night.